Gibbs Free Energy going to be the topic of this lesson. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, in addition to high school and college science prep, we also offer MCAT, DAT, and OAT prep as well. I'll leave a link in the description where you can find those courses. Now, this lesson is part of my new general chemistry playlist. I'll be releasing several lessons a week throughout the rest of this school year, so if you want to be notified every time I post one, subscribe to the channel, click the bell notification. So, Gibbs Free Energy. So symbolized by the letter G, and more commonly we're going to talk about the change in Gibbs free energy, delta G. And delta G is simply defined in terms of quantities we've already looked at, the enthalpy change and the entropy change. And this is one of the more famous equations in thermodynamics here. So delta G equals delta H minus T delta S. Now, before we get there, and technically that is kind of the definition of delta G, it turns out it's a mathematical definition. Mr. Gibbs here, in coming up with his definition, it really was just a mathematical definition. Now, what you've got to realize, though, is that when we talk about Gibbs free energy, don't think of free like it doesn't cost anything. It's not that kind of free. It's like, are you free for lunch on Friday? Are you available? So when you think of Gibbs free energy, you want to think of energy that is available to do work, energy that is free to do work. So we like talking about the interaction between the system and the surroundings. The system is whatever you're looking at, often a chemical reaction, and the surroundings is everything else in the entire universe. And so it turns out the system can't create its own energy. If the system ends up with more free energy, in this case Gibbs free energy, it's because it got it from somewhere. It's because the surroundings gave it to it. So, however, the system can use up its free energy. Again, this is the energy available to do work. And if the system uses up its free energy, it's using it up to accomplish something. And so in this case, it turns out when a system uses its energy, its free energy up to accomplish something, that by necessity means delta G is going to be a negative number, less than 0. And in this case, that's when a reaction is spontaneous. So the system can choose to use up its own energy, but can't create its own energy. And so when delta G is positive, that is a non-spontaneous process. The system can't create its own energy. The only thing it can do is get energy from the surroundings. The surroundings can give it that free energy, but it can't just create it on its own. And so big thing here is that when delta G is a negative number, that is the kind of reaction that is spontaneous, one that actually occurs. The system is using up some of its free energy to do work. But when delta G is positive, that's a non-spontaneous reaction. And then finally, when delta G equals 0, that is a system at equilibrium. So one quick thing here, we'll talk about this more later, but contrast delta G versus delta G standard. That little circle means standard, and that means talking about the delta G under a certain specific set of standard conditions. And those standard conditions mean that all reactants and all products, if they're aqueous, have a 1 molar concentration, or all reactants and all products, if they're gaseous, have a 1 atmosphere partial pressure. Now, technically, standard conditions doesn't imply a temperature, but most of the time, like when you look up, thermodynamic properties, say in the back of your textbook, they're going to be recorded as at standard values at 298 Kelvin, i.e. 25 degrees Celsius. And so because standard values for these thermodynamic quantities are most commonly reported at 25 degrees Celsius, a lot of students come away with the impression that the temperature is part of those standard conditions, but I'll remind you, it's technically not. You can have standard conditions at any temperature. The big thing is it tells you what the concentrations of your reactants and products are. Again, for aqueous species, all 1 molar concentrations. For gaseous species, all 1 atmosphere partial pressures. And so in this the last 3 lessons here are really going to be dealing with delta G in this thermodynamics chapter, and so I just really want to make sure you distinguish between these two. That'll be important later on, and sometimes as professors, we don't do a good job of it either. So right now we're talking about plain old delta G here. So what we're saying here is that when delta G is negative, it means that the reaction is spontaneous under whatever conditions you happen to be under that this value applies. When it's positive, non-spontaneous, when it's at, equal to 0, you're at equilibrium. Okay, so where did Mr. Gibbs come up with this? Well, how did he come up with the idea that delta G being negative is a spontaneous reaction? Well, we learned from the second law of thermodynamics what the requirement for a spontaneous reaction was. We learned that delta S system plus delta S surroundings has got to be positive. So the delta S of the entire universe is positive for a spontaneous process. That's what our second law of thermodynamics come from. And that's actually where Gibbs began. He started with this lovely expression and said, well, that's where I'll start too then. But he took this a little bit different route here. And by the way, when you see system here, we technically don't have to label that one. If you ever see delta G, delta H, or delta S without a label, that's automatically for the system, which is often a reaction or something along these lines. But if you're going to say delta S surroundings or delta S universe, you better label those. So, but the one that's not labeled, that's the delta S of the system. Well, it turns out this would be a rather inconvenient way to figure out if a reaction is going to be spontaneous, because measuring the delta S of the system is one thing, but measuring the delta S of the entire rest of the universe, that's kind of problematic. So he said, well, you know, it turns out we could measure that indirectly, though, by just looking at the system. So if you recall in the last lesson, we learned one of the definitions of delta S was that it was Q reversible over T. Q reversible over temperature. And we also learned earlier in the course, way back in chapter 5, that enthalpy was the same thing as heat for a process carried out at constant pressure. And so as a result, we can kind of come up with an expression for delta S that is equal to delta H over T when done at constant temperature as well as constant pressure, as it turns out. So what we're going to do is make some substitutions here. So in this case, for delta S of the surroundings, we'll keep the delta S of the system. But again, this is not super convenient to try and measure it for the whole surrounding. So what we're going to do is make some substitutions here. We're going to put plus the delta H of the surroundings over the temperature. So we just substitute delta H over T for that delta S value of the surroundings. And again, this has got to be greater than 0. Well, we can take this a step further. So between the system and surroundings, we're just exchanging enthalpy. And so in this case, if enthalpy, which we most closely associate with heat, leaves the system, that's a negative value for delta H. And for the surroundings, it would gain the exact same amount and be the exact same value, but positive. And so it turns out the delta H of the system and surroundings are equal in magnitude, just having the opposite sign. And so you could substitute in, you could say that the delta H of the surroundings is equal to the negative of the delta H of the system, which again, we don't actually have to include that label. And so we can rearrange this just a little bit further and go delta S plus, we'll put a negative sign in there, negative delta H of the system, I'll erase that in a second, just FYI, is greater than 0. And so once again, we don't actually need to label the system, so we'll take it off. So, but the interesting part here is that now I've got an equivalent expression to the second law of thermodynamics at the requirement of a spontaneous reaction, that delta S minus the delta H over T has got to be a positive number. Well, let's rearrange this just a little bit. So what we're going to do is we're going to multiply through by negative T. And so we're going to get negative T delta S plus delta H. And when I multiply 0 by negative T, I still get 0. So, but I did mess up one thing. If you multiply or divide by a negative, it changes the sign here. So it becomes a less than sign instead of a greater than sign. And so we end up with this expression right here. So and if we rewrite this just the opposite way, delta H minus T delta S is less than 0. And again, we derive this from the second law of thermodynamics. This is a requirement for a reaction to be spontaneous, something that's true for any spontaneous reaction or process. And so Mr. Gibbs thought this was rather convenient, so that now instead of having to measure anything involving the surroundings, I can just measure the enthalpy change of the system and the entropy change of the system and not have to measure anything in the surroundings at all and come up with a requirement for a reaction to be spontaneous. And it turns out when this lovely quantity is a negative number less than 0, that's when a reaction is spontaneous. He said, well, you know what? I'm just going to call this combination of things delta G. And that's where Mr. Gibbs came up with this idea. So the derivation of this is not super important. For those of you that are interested, that's where it kind of comes from. But you do have to know this equation. Delta G is equal to delta H minus T delta S. And sometimes I like to be facetious and shock some students. I'll be like, hey, I talked to your professor the other day, and you guys need to get higher test scores. So, and it turns out I didn't talk to their professor. I didn't know their scores, but they need to get higher test scores. Just a way of remembering that equation, because that equation for Gibbs free energy is super important. So now we know what Gibbs free energy is. It's a mathematical equation. We know where it comes from, but we know what it means. When delta G is negative, a reaction is spontaneous. When delta G is positive, a reaction is non-spontaneous. And when delta G equals 0, the reaction's at equilibrium. One thing to note, so if delta G is negative in one direction, so then the opposite direction of the reaction, delta G, would be the exact same number, but positive. And so another way of saying delta G is positive means a reaction is non-spontaneous. Well, it also, you could just say, well, the reverse reaction is the one that's spontaneous. So you could say it that way as well, just an FYI. So now we're going to talk about some relationships between delta G, delta H, and delta S, and some conditions for when a reaction is going to be spontaneous or not. So we're going to rely back on this equation first, but before we look at this mathematically, it might be helpful to kind of talk about what the universe wants in a chemical reaction. And it turns out the universe wants a couple of things. It wants one, we want to know that free energy needs to go down. Well, it turns out from an enthalpy perspective, your best bet to have your overall free energy going down is to have your enthalpy go down as well, to give off heat, so to speak. And so exothermic reactions tend to be much more likely to be spontaneous than endothermic reactions, but that's only part of it. But that's one of the things the universe wants. It wants delta H to be negative, wants the reaction to be exothermic and give off heat. Now, on the other side of the coin, it turns out that we learned from the second law of thermodynamics that one of the big things the universe wants is, so for a spontaneous process, the entropy change of the universe is going to be positive. It's going to increase. So in terms of entropy, well, great way to get a good start on that is just if the entropy of the system is increasing as well. And so the second thing the universe wants, in addition to having an exothermic reaction and a negative delta H, is it wants a positive delta S for that reaction, a positive delta S of the system. So, and it turns out if you give the universe both of those things, that reaction will always be spontaneous. If you don't give the universe either of those things, like let's say instead of an exothermic reaction, you have an endothermic reaction. And instead of delta S of the reaction being positive, delta S of the reaction is negative. Well, for an endothermic reaction where delta S of the reaction is negative, that reaction is never going to be spontaneous. So, and then finally, if you give the universe one out of the two things it wants, either it's exothermic but delta S is negative, or it's endothermic but delta S is positive, well, it turns out then that reaction will be conditionally spontaneous. It will be spontaneous under certain conditions. But you've got to give the universe at least one of the two things it wants. So, and again, the universe wants things to be lower in energy, and so things that give off heat, more likely to be spontaneous, so exothermic reactions. And if you looked around my office here right now, you'd find out that the second law of thermodynamics is definitely in effect. It's more likely to, on its own, get messy rather than to get clean. And the universe likes more disorder and things of a sort. And so again, second thing the universe wants is a delta S that is positive for the reaction, for the system. All right. So let's take a look at this mathematically now. And before we get too far into this mathematically, we got to make sure your math skills are up to speed. So my question for you is, what do you get when you add a positive number to another positive number? Yeah, you get another positive number, an even bigger positive number. Now, let's not go, assume too much here. What do you get when you add a negative number to another negative number? Great, you get an even more negative number. Now the difficult one. What happens when you add a positive number to a negative number? Well, it depends. And notice I didn't say multiply. We're not multiplying here. We're just adding. If I add a positive number to a negative number, well, the result could come out positive, negative, or zero, depending on if one's bigger than the other. If the positive number is bigger, well, then adding them together gets positive. If the negative number was a higher magnitude, then it's overall going to come out negative. And if they were exactly equal in magnitude, then they'd add up to exactly zero. These are the math skills you need. And so when we take a look at this delta G equals delta H minus T delta S, we're going to look at this as A plus B, where A is simply delta H. But B is not simply delta S. It's this entire second term, including the negative sign. It's negative T delta S. And what you should realize about this second term here is that it's always going to have the opposite sign of whatever delta S is. Because the temperature here, it turns out, has to be in Kelvin. And there's no such thing as a negative temperature in Kelvin. It stops at zero. So on the Kelvin scale. So, but you got this negative sign over here. And so if delta S is positive, then this whole term is going to end up negative due to that negative sign right there. And if delta S is negative, well, a negative times a negative would be positive, and this whole second term is going to end up positive. And so now we can evaluate based on the signs for delta H and delta S, we can look and say, well, when would delta G come out negative? Because again, that's when the reaction would be spontaneous. So let's give the universe both of the things it wants. And the first thing the universe wants, it wants an exothermic reaction, and it wants the entropy change of the system, of the reaction, to be positive, again, as a contributing factor towards the entropy of the entire universe being positive. All right, well, if we look at this then, this means that A, our first term, is negative. So, and then B, if delta S is positive, well, again, a negative times a positive means that B is going to come out negative as well. And if you add a negative number to a negative number, you're going to get a negative number no matter what. And when we say no matter what we really mean is no matter what value of the temperature you plug in. Again, you can't plug in a negative number for temperature because it's on the Kelvin scale. So T is either going to be 0 or it's going to be a positive number, but it can't be negative. And so no matter what possible temperature you plug in here, you're just still adding two negative numbers. Now it turns out at low temperatures, this would be a small negative number, and at higher temperatures, this ends up being a large negative number, but it's a negative number either way, and a negative plus a negative is going to be negative, period, no matter what temperature we talk about. And so when delta H is negative and delta S is positive, when you give the universe both of the things it wants, that reaction is going to be spontaneous, we say, at all temperatures. That's kind of how that works. Now, what happens if you don't give the universe anything that it wants? So in this case, what if we say that delta H is positive and delta S is negative? So if we go back and take a look at this situation now, we said earlier, you got to give the universe at least one of the things that it wants. If you don't give it either one, it has no chance of being spontaneous. And it turns out this is not going to be spontaneous at any temperature, as we'll see. So, but in this case, delta H is positive, so A here is a positive number. And with delta S being negative, that means that negative T delta S, that whole second term, well, again, a negative times a negative is a positive. And I don't care if we're doing this at low temperatures and the second term is a small positive number, or at high temperatures and the second term is a large positive number. I'm adding two positive numbers in either case, and delta G is going to come out positive no matter what. And if delta G is positive, that reaction is non-spontaneous. So a couple different ways you could phrase this as well. You could say it's non-spontaneous at all temperatures. You could say that it's spontaneous at no temperatures, not usually the way we say it, but you could also say that it's the reverse reaction that would be spontaneous at all temperatures as well. All right, finally, some conditional things. So let's say that delta H and delta S are both positive or both negative. And in both these cases, you're giving the universe one out of the two things it wants, which means we're going to see some conditional spontaneity in these cases. So let's take a look at this for a sec mathematically. So if delta H is positive, then our first term here is positive. And if delta S is positive, it means our second term here is going to be negative. Now, if my goal is to get a spontaneous reaction, then which one of these terms do I want to dominate? Well, again, I want delta G to come out negative, so I want the negative term to dominate. So, and it turns out that delta H and delta S, as long as you don't change the temperature too drastically, the values for delta H and delta S don't fluctuate a lot. So the big place this equation is going to change then is by changing the value of the temperature you plug in, again, in Kelvin. And so in this case, I can make this a very large negative number by putting in a very large temperature. I can make this a very small negative number by plugging in a small temperature. And so the key is which one has got a better chance of having delta G come out negative. Well, again, I want the negative number to be bigger than the positive number, and the negative one's the one with temperature. So let's make this a large temperature. And so it turns out when delta H and delta S are both positive, we like to say spontaneous at high temperatures. Now we have to be careful. What do we mean by high temperatures? Well, it just means over some threshold temperature, just over some threshold temperature. And that may be something you consider high, it may be something that you don't consider high, but it's not about you or me. It's about the reaction of interest. So let's say we took a look at, say, H2O solid going to H2O liquid, and H2O liquid going to H2O gas. Now, if you look at this, and we'll start with the second one first, and going from a liquid to a gas, we're gaining moles of gas. And we learned earlier in the chapter that if you increase in the number of moles of gas, it's definitely going to have a positive delta S for the reaction or process. So in this case, that's definitely got a positive delta S. But again, to boil something, to go from liquid to gas, definitely takes heat. And so it's an endothermic process. And so we've got exactly one of these scenarios where we've got an endothermic process that results in an increase in entropy for the system. Delta H and delta S are both positive. And you very well know that to be spontaneous, to boil water, at least at 1 atmosphere pressure, you've got to have a minimum temperature of 100 degrees Celsius. It's got to be over 100. Anything less than 100 degrees Celsius, it's not going to be spontaneous. Anything over 100 degrees Celsius, it will be spontaneous. And so in this case, when we say spontaneous at high temperatures, we mean spontaneous above some threshold temperature, in this case, 100 degrees Celsius or 373 Kelvin. Same thing here with going from solid water, ice, to liquid water. So in this case, it's going to be all about 0 degrees Celsius, right? Which maybe you don't consider high, and I definitely don't consider it high living in Arizona, but it's not about you or me. So in this case, it's all about just being above some threshold temperature. And so in this case, for the process of melting, for this case, water, you've got to be above 0 degrees Celsius, not below. Any temperature above that would be considered a high temperature for the melting of water, and any temperature below 0 degrees Celsius would be considered a low temperature for melting of water. So that's kind of how that works. So I just want to make sure when you see the word high here, you don't think about what you personally consider hot or cold. All right, if we go one step further, and by the way, one thing to note here, I want to clarify on that high temperature. If you were asked to calculate what temperature that is, well, again, the key is, if we looked at, like, say, again, the boiling of water. So if you plug in the delta H for vaporization and the delta S for vaporization of water, well, it turns out if you plug in any value of T higher than 373 Kelvin, again, these got to be put in Kelvin, so higher than 100 degrees Celsius, which is 373 Kelvin, then delta G is going to come out negative. If you plug in any temperature lower than 373 Kelvin in for T, then delta G would come out positive. And if you plugged in exactly 373 Kelvin, that's when delta G would come out to 0. And so oftentimes you're asked to find that threshold temperature. And so to find that threshold temperature, you just set delta G equal to 0, and then plug in the value for delta H and delta S, and then solve for that temperature. It comes out in Kelvin. Now we'll see some examples of this later. You just got to be careful on your units, because delta H is usually given in kilojoules per mole, but delta S's are usually a lot smaller than delta H's, and those are usually given in joules per mole Kelvin. And so with this being in kilojoules per mole, but this only in joules per mole Kelvin, you either got to make them both joules or both kilojoules before you start doing your calculation. All right, so last scenario here where delta H and delta S are both negative. So if delta H is negative, well, that means definitely our first term is simply negative. But if delta S is negative, again, a negative times a negative means your second term is positive. And again, that second term here, that whole negative T delta S, is always going to have the opposite sign of whatever just plain old delta S has. And so in this case, again, we're adding two numbers. One's negative, one's positive. If my goal is to come out with an overall negative number, that way delta G comes out negative and the reaction is spontaneous, well, then I want the negative term to have the larger magnitude. Well, again, I can't really change the value of delta H in any significant way, but the second term has temperature in it, and in this case, I don't want to make it as big as possible. I want to make it as small as possible. That way the positive term will be smaller than the negative term. And so in this case, I want to limit the size of it by lowering the value of T I plug in. And so here we'd say that the reaction is spontaneous at low temperatures. And again, it's not what you or I would necessarily consider low. It's just mean below some threshold temperature. And so instead of melting ice, what if I wanted to freeze liquid water? Well, freezing liquid water is spontaneous below 0 degrees Celsius. It's non-spontaneous above 0 degrees Celsius. That's kind of how it works. So low in this case would just mean below 0. Well, what if I wanted steam to condense into liquid water? Well, again, steam will condense into liquid water if you're below 100 degrees Celsius. So would 90 degrees Celsius be considered a low temperature in this case? Yes. Now, do you personally consider 90 degrees Celsius a low temperature? No. So again, it's all about, is it below the threshold temperature for the given reaction you're looking at? Cool. You've got to know these four situations and when that reaction is going to be spontaneous, either at all temps, no temps, high temps, or low temps. Now, a lot of students simply are just going to memorize this chart, and if you want to go that route, fantastic. So, whereas some students will actually work out the math every time in such fashion, and I personally do it that way myself. Well, truth be told, I kind of have it memorized now as well. So, but I personally like that way. So, but I usually get about half students working out the math, half the students just memorizing this chart. Whichever one makes more sense for you personally, go with it. But at the end of the day, you are definitely on the hook for knowing, given the sign of delta H and delta S, under what conditions that reaction is going to be spontaneous in terms of temperature. So the first problem we're going to look at is you're given a reaction here, N2 plus 3H2 going to 2NH3. You're given the delta H for this reaction, and then you are asked whether or not this reaction is spontaneous at all temperatures, no temperatures, high temperatures, or low temperatures. And so obviously you're just supposed to match it up with one of these four scenarios. Well, right off the bat, you're told delta H is negative. It's an exothermic reaction. You know that for sure you're giving the universe one of the two things it wants. The question is, what is delta S? Because unfortunately, delta S was not provided. However, in the last lesson, we learned how to predict the sign for delta S. And the single most important factor was change in moles of gas. And we're definitely going from 1, 2, 3, 4. These are both gases. So 4 moles of gas ending up as 2 moles of gas. That's an overall decrease in the number of moles of gas and therefore a definite decrease in entropy. That tells us that delta S is negative. And so as a result, we've got delta H and delta S both being negative. And that reaction is definitely only going to be spontaneous at low temperatures. And again, if you want to look at this kind of mathematically, you go back here and say, okay, if delta H and delta S are both negative, well, then my first term is negative. But a negative times a negative means my second term is positive. And if I want the negative term to win, so that delta G comes out negative, then I want to limit the size of the second term, which means make that temperature small. And so that's where we get this idea of it being spontaneous at low temperatures. All right, that is the first example of problem. Let's do a little bit of math here as well. Okay, so first thing I want to look at is phase changes with regard to delta G, delta H, and delta S. And so it turns out when you are at a phase change temperature, like the boiling point or the melting point, aka melting point, same thing as the freezing point, FYI, it turns out you have two phases in equilibrium. At the boiling point, you have liquid and gas in equilibrium. At the freezing or melting point, you have solid and liquid in equilibrium. And so having them in equilibrium means that delta G equals 0 at the phase change temperature. Well, if we look at what that implies then, we could say that 0 equals delta H minus T delta S. So, but again, in this case, let's say we're doing this in this problem, we're given the delta H of vaporization and the delta S of vaporization. That means the temperature at which this is going to be true is going to be the boiling temperature. And then we can rearrange this. And notice we can just take this delta H vaporization on this side, and on this side we'll add T times the delta S vaporization, and then we'll divide through by that boiling temperature and get that the delta S vaporization equals the delta H of vaporization over the boiling temperature. So, and that's where this kind of comes from. So, and you can do it again for any phase change. So at any phase change, delta G equals 0, and we can derive expressions like so. So, and as a result, you've now got two equations. They've got three variables, and if I give you two of them, you should be able to calculate the third, which is what we'll do in this next problem. It says, for water, delta H vaporization is 40.68 kilojoules per mole. Delta S vaporization is 109 joules per Kelvin mole. What is the boiling temperature of water? So we're wanting to get this boiling temperature. So in this case, we can rearrange this and get that the boiling temperature. So we'll move this up and then we'll divide through by the delta S vaporization, but it's going to equal the delta H of vaporization divided by the delta S of vaporization. And again, both these values were provided. Now we got to be a little bit careful. Delta H vaporization was given as 40.68 kilojoules per mole. The delta S was given as 109 joules per Kelvin mole. So whether it's joules per mole per Kelvin or joules per Kelvin mole, same diff. So, and then we can calculate that, and we'll see that that's where the Kelvin part is going to come from. So we need all the other units to cancel, though. And the moles part, that's great, but kilojoules and joules, those aren't going to cancel each other out. And so here's, again, one of those places you got to be careful. In fact, delta G and delta H are most commonly reported in kilojoules because they're significantly larger than delta S, which is only reported in joules per Kelvin. So it's kind of like if I said, hey, how tall are you? And you said, 6 foot tall. And I said, no, how many miles tall are you? And you just kind of looked at me funny because you probably have no idea how many miles tall you are. Some, 0.015 or something miles tall, or maybe probably smaller than that actually. So, but we don't know. We would never measure our height in miles. That would be the most inconvenient unit ever. Well, same thing it turns out for delta S. Delta S, we wouldn't use kilojoules because here instead of being 109, it would have been 0.109. And so it's much easier to, instead of talking about fractions, to talk about whole numbers. And that's why for delta S, which is usually much smaller than delta G and delta H, we'll use joules per mole Kelvin instead of kilojoules. But it does mean that when you're starting to do some calculations, you need to check your units. Put everything in kilojoules or everything in joules. It's your choice. It'll work out the same either way, but you need to go there. So we need to change some things here. And personally, I like changing kilojoules to joules. Instead of 40.68, we're going to have 40,680. Let's make that 8 look a little better. And now that's in joules rather than kilojoules. And now we're ready to do a little bit of math. Let me grab my calculator. All right, so 40,680 divided by 109 is going to give us 373.2 Kelvin. Which would be right around 100 degrees Celsius. Now, obviously, you could have been like, Chad, I already knew the boiling temperature of 100 degrees Celsius. Why would I have ever done it this way? That is a great question. Why would you have ever done it this way? You should have been like, I know that one. So, but odds are they're going to give this, kind of a calculation for something other than water. And I'm guessing that you haven't memorized the boiling temperatures of every known liquid, right? So, but I wanted to work one out for one that you did know just to show you how it worked out. And again, the big things here is that when you solve for your temperature, it's going to come out in Kelvin. So your delta H and delta S have to either both be in joules or both in kilojoules for this to work out properly. So, but oftentimes the professor loves to get you this far. Not only could you have made a mistake and not making your units match, but then once you get the right answer, they might put 373 degrees Celsius as one of the answer choices on the test. But it's not 373 Celsius, it's 373.2 Kelvin. The correct answer in Celsius would have then subtract off 273 and been 100 degrees Celsius. So be careful. A couple different ways professors can kind of give you some good detractors to throw you off on just such a calculation. Now, if you found this lesson helpful, a thumbs up button and a comment are the best things you can do to support the channel. And if you're looking for practice for your general chemistry course, take a look at my general chemistry master course. It includes over 1,200 practice questions. I'll leave a link in the description. A free trial is available. Happy studying.